Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. So, this is a course called Games and Information. In IIT Bombay, it runs under the course code SC 631. So, what is this course about? This course is about the theory of games, but with a particular emphasis on issues related to information in games. Okay. So, in that regard, there are some other courses also on games, but this course is very different in the particular emphasis that it has on the role of information. Okay. So, what I will do is, of course, I will not assume any background in games. So, what I will be doing during this course is I will start off from the basics of game theory, introduce you to at least the elementary aspects of static games, where information is really trivial and does not play as important a role. And then we will ramp up very quickly to games where information is an integral part of the game definition and the game solution. All right. Okay. So, to begin with, let us start with what is a prototypical example, one of the sort of famous games that is often referred to in books on game theory and even in popular literature, which is the game called Prisoner's Dilemma. What is the Prisoner's Dilemma? Prisoner's Dilemma has the following situation. So, there are two prisoners that are held in solitary confinement. They have both been convicted, or they have both been suspected, let us say, of a crime. Okay. Now, they have been held in solitary confinement, and the judge offers them a certain deal, you can say. The judge offers them a deal, which is to say that, well, you can, if you want to, you can testify against the other prisoner. Okay. So, there are, let us say, two prisoner A and prisoner B, and the judge offers them the following deal, that if you testify against the other prisoner, then you have the option to testify against the other prisoner. Okay. Now, based on what happens, in the sense that based on what both prisoners do, you will get a certain number of years in jail. That will determine your punishment. So, if I have to write out how many years in jail you are going to get, it can be written out in a sort of like a matrix like this. So, the prisoners have the option to testify. So, they can either testify or stay silent. So, if prisoner A stays silent, so he has two options, to stay silent or to testify, and likewise prisoner B also has the option to stay silent or to testify against the other prisoner. Okay. And the deal is like this. So, now if both of you remain silent, okay, that neither testifies against the other, then both of you would get 1 year in jail. Okay. So, the way I have written this is 1, 1, which means the first term here is the first one here is the number of years in jail for A, and who is on the rows here, and the second term here is the number of years in jail for B, who is on the columns. Okay. So, if they both stay silent, then they each get 1 year in jail. If one of them stays silent and the other testifies, okay, so in this case, for example, I am now writing if A testifies and B stays silent. Now, if A testifies and B stays silent, then the one who testifies goes free. So, he gets 0 years in jail, and the one who stays silent gets 3 years in jail. Now, we can of course debate on whether this is fair or not fair and so on, but that is not our mandate here. We want to be able to reason about this situation. That's what we want to do. So, symmetrically here, so naturally now if A stays silent and B testifies against A, then A will get 3 years in jail and B will go free. And then the judge says that if both testify, then both of you would get 2 years in jail. Okay, so if each testifies against the other, then each of you would get 2 years in jail. Now, this is an example of a game. So, what is special about this? You can see the first thing you notice is that no player a player obviously has a clear objective here, which is that he wants to get as few years in jail as possible. But there is the objective is not well defined for him, because it depends, the number of years he will get in jail depends also on what the other one does. So, the number of years in jail that a player gets depends not just on what he chooses to do, but also on what the other player chooses. And this is the same, this is the case for each player. So, consequently, there is a linking of decisions that is happening here, where neither player can decide what he can do without taking into account what the other player is also going to do. Alright. But then remember the assumption that we started with. We started with the assumption that these players are held in solitary confinement, which means that they don't have the option to discuss between themselves on what their strategy is going to be. Right. This is a classic example of a game. Now, you might think that this is something very contrived or artificial, but this is exactly how decision making happens when, say, competing firms try to decide what their strategies are going to be, or two generals from opposing armies would try to decide what their strategies are going to be, and this is exactly how the payoff gets played out. The reward that one gets depends not only on what you do, but also on what the other person does. All right. Now, what we want here is to answer this in some sort of a logical, with some kind of a logical framework, and that is what the theory of games attempts to do. It attempts to come up with a framework for reasoning about these situations. Right. So let me ask you here, how would you reason about this problem? So here is one way of reasoning about this, and this is this is a special structure in this particular problem, and it's also one of the reasons to start off with this problem. You can see there is the structure here is that if you look at the strategy of any one player, each player has two strategies. Okay, I'll make this more formal, but each player has basically two strategies, either to stay silent or to testify. Now, you compare the corresponding rewards that the player would get if he plays one strategy or the other strategy. And what you observe is that testifying is always better than staying silent, regardless of what the other player does. So, for example, here, so if the other player if B is staying silent, then testifying is better than staying silent for A. If B is going to testify, then again testifying is better than staying silent for A. And this is the situation is symmetric. So naturally, therefore, similar reasoning can be applied for B also, and so consequently, it makes sense that both players testify. All right. So this is one line of reasoning. This line of reasoning is essentially saying that what I am looking for is a strategy that is uniformly better than all other strategies, regardless of what the other player does. So, in other words, I am making the interlinking of decisions irrelevant here, right? The fact that there is another player involved and what the other player is going to do affects my payoff, all of that is becoming irrelevant. What is happening, what I am trying to do is find a strategy which outperforms the other strategies, irrespective of what the other guy does. Now, that is applicable in this game, and that is applicable because of the way these numbers are. Okay, you can imagine another type of situation in which, firstly, where these numbers aren't so aligned such that testify will always turn out to be better than staying silent, regardless of what the other person does. Okay, that could very well happen. I can come up with numbers like that, right? So your line of reasoning, therefore, cannot change case by case or game by game. You need a universal logic, because then it is a logic, otherwise it's a hack, right? You need a logic which will be applicable across all games, regardless of what the kind of coincidences that are present in the numbers of that particular game. right? So now tell me, how would you reason about this?
And let's say if I do testify, then I get to the last time. I get 2 years instead. So in either case, objective is getting full confidence, so often
No, so that's more or less the same reasoning that you had earlier. So there's also another subtlety here. So I'm not asking you how you would play this game. Okay, so there are two different types of questions we can ask in a game. You can ask the following. First question is, you can ask the question, what will each player do? Okay, the emphasis being on the word will. Okay, the other question is, you can ask is, what must each player do? What is the difference between these two? The difference between these two is, what will each player do is asking for a prediction. I'm asking you to predict what each player would do, right? It's like asking you to tell what the future is going to look like, right? It's what will each player do. What must each player do is not asking for a prediction. What must each player do is asking you for what the law is. What should be the right thing for the player to do. Okay. So what we are now in game theory, we are not interested in the first question. We do not intend to predict, although game theory can be used to predict, but we do not intend to predict what is going to be the outcome of a game. All right. What we can, we do not really know what each player would do. I mean, if I gave you two different two human prisoners like this, or two armies, or two companies, or any of that, we really do not have are not in a position to say what will each of them do. We can only guess what each of them will do, right? No, not necessarily. Not necessarily, but the point here is, this is in fact the subtlety here. What will each player do is really not our business. Okay, they are they have free will. They may do whatever they want. Okay, what each player ought to do, assuming a certain set of axioms, is what we want to try and answer. Right. So it is in many ways, game theory, what it is trying to do is come up with a sort of a set of laws, a set of laws and a set of reasoning rules by which we can reason about situations like this. Okay. So given the bunch of reasoning rules, if you follow through those rules, you should be able to say what each player must be doing. All right. And hopefully the answer is sharp enough that it actually tells us that, okay, here is exactly, this is the precise thing that each player must be doing, and therefore that is what we think is the solution of the game. All right. So now one of the most, of course, popular use cases for game theory is to use it as a prediction. All right. But whether the prediction works or not depends on whether your laws align with the situation that is actually prevalent in the game or not, essentially. Okay. So the central quest in the theory of games is not to predict. It is rather to reason. Okay. So what this means is, we cannot say what will happen. So we confine ourselves to saying what is logical. Okay. So that is, and what should be the train of logic is the thing that we are asking ourselves. Okay, that's essentially the question at hand. Okay. So now that we know that this is what we want to answer, we would like to ask, okay, if we want to answer what must each player do, we basically would like to see, okay, what should be our reasoning rules for this. Okay. So this requires us to basically set up a set of axioms. Okay. One axiom is actually automatic here, implicit in this problem formulation, and that axiom is that each player is looking for the least number of years in jail. Okay, so that is effectively one axiom, and in fact, this is the underlying basic axiom across all of game theory, that there is a function or a payoff function or a cost function or something like that, which each player is looking to optimize, and what a player is basically interested in is the least value of that particular function. Okay. Now, of course, as I said, this function is not well defined until I also tell you what the other player is doing. So, it is not really a function, but it is a family of functions that each player has, right. The other thing that is implicit in the problem formulation is that each player, these prisoners were held in solitary confinement, which means that the underlying assumption here, the axiom here is that players cannot communicate with each other. Right. So, there is no way for players to communicate and or discuss what each of them would do, right, and the absence of a communication medium actually is an underlying assumption in this. So, suppose if I told you, so just to see why this is the case, suppose if I told you the other case, suppose I told you that the players could discuss amongst themselves and come up with a strategy on what to do. What would they play? No, let's say they want to. The problem is symmetric, right? So they want to take, say, let's say the sum total of the years in jail or something like that. So the question is, if both players were allowed to communicate with each other, okay, would they necessarily play silent? Okay, now in this case, that answer is correct, but I will tell you there is a subtlety here. It could very well happen that both players talk to each other, each player convinces the other that I am going to stay silent, but when it comes to actually pressing the button, he goes back and presses testify, having convinced the other person to stay silent. No. So pre-play communication, okay, has an important role in this, because by talking you into it, I could potentially influence you to stay silent, and then having done that, it then becomes optimal for me to testify. Okay, so again, there is a subtlety here, which is that just communication is not enough. I can say I am going to stay silent, but what is the guarantee that I will stay silent? Okay, the issue is not just communication. Communication is important, but alongside that, what is also important is a mechanism to enforce an agreement. Okay, what is called a binding agreement, some mechanism by which players, when they say that this is what they would do, that is what they would actually do. Okay, so if you have such a mechanism, okay, now what such a mechanism means, how do you make that formal, etc. All of that is part of the theory of games, okay, and that needs development. Okay, this is not I'm not telling you a sort of sociological story. Such a thing can actually be made formal. What exactly is such a mechanism? What exactly do we mean by pre-play communication? How much is that communication, etc., etc. All of this can be made formal, but once that is made formal, it does turn out, if you give players both the option to communicate with each other and to enter into binding agreements, then yes, it is indeed the case that they should both remain silent. Okay, that is the point on which, that is the agreement that they will end up signing, which is that I will stay silent and you will also stay silent. Now, the mechanism to enter into binding agreements requires sometimes a mediator. Okay, so I need to introduce a third player, C, here, who will be the one that creates these alternatives, gets them to agree, etc., etc., which is, all of this is too early to get into this course at this moment. But remember, there is this subtlety involved here, and what this is also telling you effectively is again the second thing, the thing that I mentioned about the course, which is the role of information. When there is no communication channel between them, the problem has a very different character from when there is a communication channel between them. Okay, and moreover, when the communication channel passes through a mediator or does not pass through a mediator. All right, all of these are this is part of the axioms of the game. Now, the way I presented this particular problem to you, I said that players are obviously self-interested. They would each like the least number of years in jail, and that they cannot communicate with each other at all. Okay, so actually, if you see, the theory of games bifurcates itself into two different categories. So, games can be categorized into two broad categories. The first is non-cooperative games. Non-cooperative games means a game is said to be non-cooperative if players have or players cannot communicate. So, this is when players cannot communicate with each other at all. Okay, that is, so the prisoner's dilemma game that I just showed you is a game, is a non-cooperative game. The other extreme, this is not the negation, but another extreme is when there are cooperative games. Cooperative games are when players can communicate with each other, and enter into binding agreements. These are, remember, two different extremes. They are not negation of each other. Just because you cannot communicate doesn't mean that you can communicate to any extent and also get into binding agreements. Okay, so these are two different extremes. In between these two extremes lie a whole number of there's a huge gray region here in between. Okay, the gray region is where some amount of communication is allowed, but binding agreements are not allowed. Or agreements are allowed, but mediators are not allowed, etc., etc. Various types of exotic combinations are possible in between these two, and all of those are very interesting, very fascinating, but also quite a bit of that remains open. Okay, so it's not fully resolved as well. But these two being extreme cases, in science, it's often the case that when you cannot solve a general problem, but you can solve corner cases. The corner cases often are become the way to anchor your further theory. So, these are extreme cases that have been fairly well resolved now. Okay. So, for most part of the course, we will actually focus on only non-cooperative games. Okay, so we'll consider games of various kinds that are, but all of them will have a non-cooperative flavor. Yeah. No. So, are cooperative games mere optimization problems? Not necessarily. Okay. Because of course they can be posed as optimization problems, but so one of the criteria for the solution of a game in a cooperative setting is that there is some kind of a let's say a combined optimal being asked for. Okay, but that is not the only criterion. Okay, so see, for example, the particular emphasis here is the issue of binding agreements, right? So again, this is a slight digression, but I will just mention this. This is an important issue because we need to also factor into our way of reasoning about the game. When we reason about this, we need to factor in what happens if there is no agreement reached. So, what is the disagreement fallback option that both players have? Once you factor that in, it becomes a much more sophisticated thing than just, trying to do a collective sum, optimization of the sum of the pair. So it is not a straightforward optimization. No, not necessarily. So this is part, if they can enter into binding agreements, they need not. Right. So what happens if they do not agree is something that they are always mindful of while trying to agree. Right. So this is part of the way we go about reasoning about this game. Again, so I should also mention, since we are on this topic, so I should also mention another thing here. See, cooperative versus non-cooperative doesn't necessarily mean conflict or non-conflict. Okay, so cooperation, non-cooperation, a non-cooperative game just means that players cannot communicate, but it doesn't mean that there is necessarily a conflict in the game. All right. So they cannot communicate with each other, but that doesn't mean they are out to kill each other. Okay, doesn't mean that there is a conflict in the game. So, for example, a game where there is no conflict, but there is still, you can still think of it as a non-cooperative situation, is a game where industry standards are being decided. Okay. Now, industry associations are usually you have industry associations for each segment. There will be an association that creates, say, the hardware, another association that makes the software. But unless they agree on a standard, they will not be able to each get the best outcome for both of them. So, for example, like for you guys, probably this is not you are probably not as exposed to this, but there was a time when CD drives and DVD drives were being introduced. What should be the radius of such a drive, the physical radius? Someone has to define this standard, right? That it is 3.5 centimeters or something like that is the radius. So the CD manufacturer may prefer one kind of radius. The one who makes the reader of that drive would prefer another type of radius. They would each want to arrive at some standard, because unless they work together, nobody is going to be able to use either of their devices. So they have to coordinate on a certain standard. So coordination is important, but then the situation could very well be non-cooperative in the sense that they don't want to be discussing with each other, because they will be ending up revealing what say, for example, their weak points or something like that. Okay, so a situation where industry-wide standards are being determined is a situation which is often non-cooperative in nature, but there is no underlying conflict involved. Okay. Likewise, cooperative doesn't mean that everything is, there's bonhomie either. Cooperative there could be conflict alongside cooperation. For example, cooperative games. So, a cooperative game with conflict is a game, say, for example, all these geopolitical conflicts in which people are trying to come up with an agreement on, say, what should be the border and so on and so forth. These are actually situations of conflict. All right, but you are trying to, but it is because you are discussing and because there is eventually a pact to be signed and so on. This is actually a cooperative game. Okay, so neither of these is true. So cooperative doesn't mean. So the correct way to put it is cooperative game doesn't mean cooperation necessarily. Okay, is not equal to no conflict. Okay, so now with this, now I think we can start with a formal definition of what a game is. So this is, of course, a simple definition, because I have not yet introduced any exotic aspects of games.